In the previous session, we have discussed what are bounds of real numbers. In this session, we will be discussing more on the properties of bounded sets. So, in the last session, we have discussed what is the least upper bound and the greatest lower bound of real numbers. And in this session, we can see that every bounded subset of R that has an upper bound and has a lower bound possess a supremum and infimum in R itself. Let us see the completeness property or the supremum property of R, which is stated as follows. Every non-empty subset of R that has an upper bound also has a supremum in R. So, why is this property relevant is because suppose we have the set, say the set of all x belonging to R such that 0 less than x less than 1. So, this set is the open interval 0, 1, which can be treated as a subset of the set of all real numbers. We can see that every element of this set is definitely less than 1. So, the supremum of this set, supposing I am calling this set as S, supremum of S is equal to 1. But we can see that 1 does not belong to the set. So, 1 is not an element of the set S. So, even if a set is bounded, there is no guarantee that the supremum as well as the infimum need not be are elements of the set S, are elements of the same set. They can be outside that set as well. But in the case of real numbers, if you consider the entire set of real numbers, every bounded subset of R that has an upper bound has a supremum in R itself. It will not go beyond the set R. And that makes R a complete ordered field, because in the algebraic properties of R we have seen that the set of all real numbers satisfies all the properties of a field, and we have seen the order properties of R, and therefore R is an ordered field. And now we have a completeness property as well, and which makes R a complete ordered field. Now, using this supremum property, we can define some of the results, some applications of supremum property. The first application being, if S is a non-empty subset of R that is bounded above, and if A is any real number, then A plus S, that means it is called the translation operation. That means every element of the set is added with the number A. So, A plus S, where S belongs to S, has the supremum nothing but A plus the supremum of S. So, let us see the proof of this. We are given the set S is equal to, proof of application of supremum property. We are given S is equal to the set of all elements in R such that S is a non-empty subset of R. So, we have set S as the set of all elements in R itself. It is a subset of R and S is not equal to null set. So, this condition is given. Also, it is given that S is bounded above, and therefore, by the completeness property that we have just now seen, there exists a supremum of S in R. It is an element of R itself. So, what is our claim? We have to prove that, we have to claim that A plus U is the supremum of the set A plus S, where S belongs to the set of all S. So, this is what we are aiming to prove. So, we are given that U is the supremum of S. Therefore, we are going to prove this claim. So, the first part is part A we can write. Given U is the supremum of the set S, which implies every element in the set S is less than or equal to U for every S belonging to capital S, because U is the least upper bound. Then if we add a real number A throughout, what do we have? We have S's less than or equal to U for every S belonging to S. Adding an A together, we will be getting A plus S is less than or equal to A plus U for every S belonging to S. So, what does that indicate? This means that A plus U now becomes an upper bound of the set of all A plus S such that S belongs to capital S. That is, A plus U is an upper bound of A plus capital S. Now, it is enough to prove that A plus U is the least upper bound. So, that is part B of the proof. We have proved one part, that means we have proved that A plus U is an upper bound of A plus S, and hence what does this indicate? A plus U is definitely, so what is the supremum? Supremum is the least upper bound. So, A plus U is an upper bound of A plus S implies A plus U is greater than or equal to the least upper bound A plus S. That is, A plus U is greater than or equal to supremum of A plus S. Now, it is enough to prove that A plus U is less than or equal to supremum of A plus S. Then we are done. Our proof is over. So, part B is that let us take V be any upper bound of the set of all A plus capital S. That means we are taking V to be any upper bound of this set A plus S where S belongs to capital S, which indicates that A plus S is less than or equal to V for every S belonging to capital S. Why? Because A plus S is an element of A plus capital S, and since V is an upper bound of A plus capital S, this condition is true for every S belonging to S. Now, what does that indicate? S is less than or equal to V minus A for every S belonging to S. Now, we have V minus A to be an upper bound of capital S. So, we have V minus A is an upper bound of capital S, but we are given the condition that U is the supremum of S. So, which indicates that U is the least of all the upper bounds. So, V minus A is definitely greater than U. Why? Because U is the least of all upper bounds, and we have just now shown that V minus A is an upper bound of the set S. This indicates that V is greater than A plus U. So, what does this indicate? This means that any upper bound of the set A plus S is greater than A plus U. So, this indicates that any upper bound of the set of all A plus S is greater than A plus U. So, since it is an arbitrary upper bound, we can even replace that upper bound by the supremum. So, this indicates that supremum of A plus S is greater than A plus U. So, we have two conditions now. The first condition being A plus U is greater than or equal to supremum of A plus S, and now that we have supremum of A plus S is greater than or equal to A plus U, both these indicate this is inequality number 2, whereas this is our inequality number 1. So 1 and 2 indicates that A plus U is equal to supremum of A plus S. So we are done. So that is the proof of that theorem. So the proof is given, U is the supremum, then X is less than or equal to U. This is what we have just now seen. A plus U is an upper bound of A plus S, therefore supremum of A plus S is less than or equal to A plus U, and then we have taken B to be any other upper bound, and we have shown that A plus U is less than or equal to supremum of A plus S as well, and hence you have this result. Now the second application of supremum property is to show that if A and B are two non-empty subsets of R such that A is less than or equal to B for all A element of A and B element of B, then definitely supremum of A is less than or equal to infimum of B. So we take the help of geometry to understand what this property says. So we have two subsets of real numbers. So we know that the real numbers can be represented on a real line. So we have two sets, namely set A, something like this. This is set A, and we have a set B, but remember we are given a condition that A is less than or equal to B for every element of A as well as every element of B. So where should we draw that B? We have to draw B on the right side of A. So B is somewhere here, this is your B. So B is somewhere here. So definitely all the elements of B are towards the right side of all the elements of A. And now we have to show that we are more interested in, definitely the supremum of A will be less than or equal to supremum of B, because B lies entirely on the right side of A, and infimum of A is definitely less than or equal to infimum of B, because A lies entirely on the left side of B. But we are more interested in what is the relation between these two, that is supremum of A and infimum of B. So definitely, since we have A less than or equal to B for every A belonging to A and B belonging to B, we have a result supremum of capital A is less than or equal to infimum of capital B. Now let us look at a rigorous proof of this statement. Given the condition that we are given a condition A is less than or equal to B, A is less than or equal to B for all A belonging to A and B belonging to B. So first let us fix one B belonging to B. Let B belongs to B be fixed. We are fixing a B belonging to B. Then this condition indicates that A is less than or equal to B for every A belonging to A. Now what happens? B becomes an upper bound of the set A. So this indicates that B is an upper bound of set A. Now B is an upper bound, and what is the supremum? Supremum is the least of all upper bounds. So this indicates that B is greater than or equal to supremum of A. Why? Because supremum is the least upper bound. Now we have fixed one B element of B and we got B is greater than or equal to supremum of A. So since B is arbitrary, since our choice of B is arbitrary, what do we have now? Supremum of A is less than or equal to, this is less than or equal to, supremum of A is less than or equal to B for every B belonging to capital B. Now what happens? Supremum of A becomes a lower bound of the set B. So this indicates that supremum of B, supremum of A is a lower bound of the set B. And what is infimum of B? Infimum is the greatest of all lower bounds. So, this indicates that supremum of A is less than infimum of B. Why? Because infimum is the greatest of all the lower bounds, and we have now proved that supremum of A is one of the lower bounds of the set B, and thus we have proved that supremum of A is less than infimum of B. So, that is that result. Now, the next result is for the functions. Now, a real valued function is a function which is defined on a subset of R to a subset of R. So, the range set as well as the domain should be subsets of real numbers. And in real analysis, we will be dealing with such functions only. So, a function is said to be bounded if the range set, that is f of x, the images, the set of all images is bounded in R. So, we have defined it is bounded above if the range set is bounded above, and it is bounded below if the range set is bounded below in R. And generally, a function f is said to be bounded if there exists both an upper bound as well as a lower bound. So, for simplicity of notations, we are defining a function f from A to R is said to be bounded if there exists some real number such that modulus of f of x is less than or equal to m. Why? Because this definition guarantees that modulus of f of x is less than or equal to m. We have seen in the previous session, this can be equivalently expressed as negative m less than or equal to f of x less than or equal to capital M, so that this guarantees an upper bound as well as a lower bound. So, this definition is enough to guarantee that the function is or the image set is bounded above as well as bounded below. Such a function is said to be a bounded function. Now, we have a theorem or a result showing that if f and g are two bounded real valued functions with a common domain D subset of R, and we are given a condition f of x is less than or equal to g of x for all the x values in the domain, then the supremum of f of d is less than or equal to the supremum of g of d. So, again a bit of geometry will help us to understand more. We can draw a graph. We are given the condition that f of x is less than or equal to g of x for every x belonging to D. So, that means suppose you have a function like this. Supposing your f of x is something of this shape. We do not know what the shape of the graph is. So, we are taking the function in this shape. Let this be the domain D, and we have another function, say g of x, which has the property that f of x lies below g of x for every x belonging to D. So, it can go in this same shape maybe, or it can go in some other shape, but anyway your g of x should be greater than or equal to f of x. Then what happens? You have the supremum of g of x, that is the peak, the highest value, to be less than or equal to the supremum of f of x. So, what is the supremum of g of x? Somewhere here is the supremum. This is the supremum of g of x, and here is the supremum of f of x. So, that is the result saying. So, that is quite evident from the figure itself that supremum of f of d is less than or equal to the supremum of g of d. But this does not guarantee. We have drawn a figure which guarantees that infimum of f is less than or equal to the supremum, or vice versa, supremum is less, no. So, here if you take supremum of f of d, this is the supremum of f of d. Where is the infimum of g? Infimum of g of x lies somewhere here. So, this is the lowest value of g. So, infimum of g of d is somewhere here. So, this equation or this inequality does not guarantee that the infimum of g of d is higher than the supremum of f of d. That is the next result that we have, namely, suppose that f and g are both bounded real functions with a common domain D. If f of x is less than or equal to g of y for every x and y belonging to D, then supremum of f of d is less than or equal to infimum of g of d. So, this inequality guarantees that whatever be the values of x and y be, f of x should always lie below the values of g. So, that means we cannot have a graph something like this. Our f of x can be like this, but g of x should be completely above f of x. That means we should have the entire g function should be above this supremum as well, maximum value of f as well. Then we have that result. Supremum of f of d is less than or equal to infimum of g of d. So, these are some of the applications of supremum property that we have learned, and this guarantees that the set of all real numbers is a complete ordered field. And if we take the set of all rational numbers, for example, we can see that there exists some sets which are bounded above, but they may be having a supremum which is beyond the set of all rational numbers. Say for example, we can see that square root of 2 is an irrational number, and if we consider the set of all elements rational numbers which are having the squares less than 2, then definitely it is bounded above by root 2, but root 2 does not lie in the set of all rationals. So, rationals is not a complete ordered field, whereas the set of all real numbers is a complete ordered field. So, that much is regarding the supremum property. Thank you.